This video is also going to sound very familiar because we already talked about carbocation rearrangements in SN1 reactions. Because E1 reactions, they also go through they also go through carbocations. They also can rearrange so we get more stable carbocations. The same rules apply. So when we have a carbocation that it's not the most possible stable carbocation, the molecule rearranges to go from a secondary to a tertiary carbocation, or from a primary to a secondary, or from a primary to a tertiary. But the molecule does everything possible to lower its energy. We usually know that a rearrangement has happened because our molecule doesn't look quite like the product. So like if we look at this molecule right here, where we have three methyls coming out of the same carbon, if you look at the products, one of those methyls is no longer there, right? And so that is a sign that you got a rearrangement. In the case of elimination reactions, particularly, what you get is that one of the double bonds forms in a strange position, in a position that you didn't expect. So like in the case of these ones, right? And so yes, the carbon skeletons are different. So that's exactly what it means, that the methyls, we have three methyls here, and here we only have two methyls in that same carbon. So carbocation rearrangements, the same rules apply as they applied for SN1 reactions. If the molecule can move a hydrogen, the molecule will move a hydrogen because it takes less energy to move a small hydrogen. But if the molecule doesn't have a hydrogen and it's still is a carbocation that is not as stable as it could be, like in this particular case, what will move will be a methyl, an alkyl shift, right? So first, the hydrate shift is favored, but if a hydrate cannot move, then an alkyl shift will happen, right? An alkyl shift will happen. So here we have some examples. You see, we start with this is the mechanism of the molecule that we saw a little earlier. So we start with this alcohol, and you see we have three methyls on the same carbon. But if we look at the products, you see the methyls are not in the same place. How did that happen? Well, the OH grabbed one of the hydrogens. Now it becomes a good leaving group, and that can leave because it gives us a secondary carbocation. So that's stable, but not very stable. Now what will happen is, if we had a hydrogen here, that hydrogen will move, but because we only have methyls, then one of the methyls have to move and position itself here. A tertiary carbocation is more stable than a secondary carbocation, so that's why this reaction is favored. That alkyl shift is worth it for the molecule. And so now two things can happen, starting with this same tertiary carbocation. If we grab that hydrogen right there, then we get the double bond here in the middle. But if what we get is the hydrogen in one of the primary carbons that are on the here, so these two, right? What you will get is the double bond to form on the outside of the molecule. So this one right here is going to be more stable because it's tetra substituted, and this one right here is going to be less stable because it's a disubstituted double bond. So this is more of the same. A 1-2 shift, either of a hydrogen or an alkyl, will convert a secondary carbocation into a more stable tertiary carbocation. Now, remember that in some cases, that alkyl shift could mean that a molecule can increase the ring size or decrease the ring size. You can refer to the practice that we did for SN1 reactions for some of those examples.